Welcome to this lecture of this course on computer aided power system analysis. In the last lecture, we have looked into the various elements of this matrices J1, J2, J3 and J4. We have shown that these matrices J2 and J3 are basically the null matrix when we apply some assumptions judiciously, and also we have derived the matrices or rather the elements of this matrices J1 and J4. So, today we will be again looking into these elements of matrices J1 and J4 into more detail and see that how these modified elements can help us to speed up the solution process of the load flow solution. So, what we did is that in the last lecture we have shown that this J2 and J3 are 0, and for J1 these are the elements and for J4 these are the elements. So, now what we have is that we have already shown that for this FDLF J1 into delta theta vector is equal to delta P vector. So, if we expand this, so we know that del P2 by delta theta 2, del P2 by delta theta 3 dot del P2 by delta theta n, then del P3 by delta theta 2, del P3 by del theta 3, then del P3 by del theta n dot del Pn by del theta 2, del Pn by del theta 3 dot then del Pn by del theta n. This is equal to this multiplied by this vector del theta 2 del theta 3 dot del theta n would be equal to del P2 del P3 dot del Pn, where n is the number of bus in the system that we have already seen. So, n is the number of buses in the system. So, now if we do expand this, if we now write down the expression of any Pi del Pi, so what we get? So, we get that del Pi is equal to del Pi by del theta 2 into delta theta 2 plus del Pi by del theta 3 into delta theta 3 plus dot del Pi by del theta I to delta theta I plus dot del Pi by del theta n to delta theta n. So, this is the expression we get from this matrix if we do expand this matrix equation, and then then corresponding to the ith row we get this expression. Now, what we do is we do something like this. So, if we do so we get something like this 1 by Vi del Pi by del theta 2 into delta theta 2 plus 1 by Vi del Pi by del theta 3 into delta theta 3 plus dot 1 by Vi del pi by delta theta I into delta theta I plus dot 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 1 by Vi del pi by del theta n to delta theta n. So, this is the equation we get. Now, in this equation we now substitute these relations. So, 1 by Vi del pi by del theta j, where j is not equal to I, is equal to minus Bij. So, then therefore, and for when, and also we have got that 1 by Vi into del pi by del theta I is equal to minus Bii. So, if we apply this, so then therefore, applying those equations, so applying the modified elements expressions of the elements of J1 what we get? We get 1 by Vy, 1 by Vi delta Pi is equal to minus, it would be Bi2 into delta theta 2 minus Bi3 into delta theta 3 plus dot dot dot, actually all of them would be minus. So, all of them would be minus. So, we should write as minus. So, it is minus, this is dot, then minus Bii into delta theta I, then dot 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 minus Bin into delta theta n. So, this is true for all I is equal to 2, 3 to n. So, then therefore, this we can write down for all I where I varies from 2, 3 to n. So, then therefore, if we collect all these equations together and then write in the matrix form, then what we get? So, we write that collecting all equations together, so we write collecting all equations together in matrix form, we get what we get? We get is minus B22 minus B23 dot 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 minus B2n, then minus B32 minus B33 dot 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 minus B3n, and then similarly minus Bn2 minus Bn3 dot 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 minus Bnn to multiplied by del theta 2 del theta 3 dot 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 del theta n, that would be equal to del P2 by V2, then del P3 by V3 dot 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 del Pn by Vn. So, this is the final relation. Now, this expression is very interesting because I mean we need to note down one very interesting thing is that this matrix in common parlance this is called B dash matrix into delta theta vector is equal to del P by V vector. So, this is the B dash matrix B dash into delta theta is equal to del P by V vector. So, where is what is what? So, this is nothing but this our original delta theta vector. This we denote as del P by V vector, where this is the del P by V vector, where every element is nothing but where this ith element is nothing but del Pi by Vi, and this matrix is called B dash matrix, and this matrix is a constant matrix. So, this matrix is a constant matrix, and what is this matrix? This matrix is nothing but the negative part of the elements of the bus admittance matrix. Now, because this matrix is a constant matrix and these elements are nothing but the negative are basically nothing but the negative of the imaginary part of the elements of the bus admittance matrix. So, then therefore, what we need to do is we can only form this matrix only once before even our load flow iteration starts, and for all iterations this matrix remains constant. And then so then therefore, how do we solve delta theta? We actually solve delta theta as, for example, B dash inverse into delta P by V vector. Now, because B dash matrix is a constant matrix, so then therefore its inverse is also a constant matrix. So, then therefore we can simply pre-calculate this inverse matrix even before our load flow iteration starts. Then at each and every iteration we have to only update this vector delta P and delta V, and then we will simply get this correction vector delta theta just by multiplying this matrix which we have already pre-calculated and stored with the updated vector delta P by delta V. Please note, in the original, even in the decoupled form of equation, what equation we have got? We have got equation as J1 delta theta is equal to delta P. So, then therefore, at each iteration in the decoupled form J1 inverse into delta P. Now, at each iteration this matrix J1 needs to be calculated, and because this matrix J1 needs to be always calculated at each and every iteration. So, then therefore, this matrix J1 will not be constant. Because this matrix will not be a constant, so then therefore, its inverse also has to be calculated at each and every iteration, and calculating inverse of a matrix is highly computationally intensive. So, then therefore, even in the original decoupled form, because we have to invert this matrix J1 at each and every iteration, still this is a computational intensive job. But here in this case what happens, that we have simply reduced everything to a ultimately a constant matrix B dash, which is a constant matrix, and because it is a constant matrix we can simply pre-calculate its inverse and simply store it. So, then therefore, at each and every iteration we are simply avoiding the necessity of inverting any matrix. So, then therefore, if we therefore, because we do not have to invert any matrix at each and every iteration, so then therefore, every iteration would be quite fast. Now, let us go into the second part for J4. Now, what was J4? In the case of J4, for J4 we have that J4 into delta V vector is equal to delta Q vector. So, it is del q m plus 1 by del v m plus 1 dot 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 del q m plus 1 by del v n, and then dot 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 del q n by del v m plus 1, and then dot 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 del q n by del v n. It is del v m plus 1, then dot 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 del v n, it is equal to del q m plus 1 dot 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 del q n. What is m? M is nothing but the number of generators in the system. So, we again just write it is the number of generators in the system. So, then therefore, if we do again expand this ith row, so then what do I get? We get that del q I by del v m plus 1 into delta v m plus 1 plus del q I by del v m plus 2 into delta v m plus 2 dot 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 plus del q I by del v n into delta v n is equal to delta q I. So, if we do expand as before the ith row for this matrix equation, we get this. Now, we apply this relation, for this J4 matrix. Please note here that here in this case J is not equal to I. So, then therefore, if we apply this relation here, so then what do I get? I get minus b I m plus 1 into delta v m plus 1 minus b I m plus 2 into delta v m plus 2, then dot 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 minus b I n into delta v n is equal to delta q I. What we have done? We have simply substituted these quantities, these expressions into this. So, this is true for all I varying from m plus 1, m plus 2 to n. So, then again if we do collecting all the equations, we get what we get? We get minus b m plus 1 minus b m plus 1 m plus 2 dot 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 minus b m plus 1 n, then minus b m plus 2 m plus 1 minus b m plus 2 m plus 2, then dot 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 minus b m plus 2 n, then minus b n m plus 1, then minus b n m plus 2, then dot 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 minus b n n. So, this equal to delta V m plus 1, delta V m plus 2, delta V n, that is equal to delta Q m plus 1, delta Q m plus 2, and then delta Q n. So, that is the equation. So, in power system parlance, we write this equation as B double dash matrix into delta V vector is equal to delta Q vector. So, this is the B double dash matrix, this is a matrix, this is the delta V vector, this is the delta Q vector. Again, this B double dash matrix is, again, it is a constant matrix, it is only constituting of the negative of the imaginary part of the elements of the bus admittance matrix. So, then therefore, from this equation we can write down that delta V is equal to B double dash inverse into delta Q. Now, because B double dash matrix is a constant matrix, so then therefore, we can always pre-calculate this constant matrix even before our algorithm iteration starts, and we can also take the inverse of this constant matrix and pre-store it. So, then therefore, at each and every iteration for updating this vector delta V, we really need not perform any kind of matrix inversion. We can simply use this pre-stored invert matrix, which is nothing but the inverse of this B double dash matrix, and then simply multiply this inverse matrix with this most updated delta Q matrix. Please note that in the original decoupled form, Z4 into delta V is equal to delta Q, and here delta V would have been J4 inverse delta Q. Now, because this matrix J4 has to be recalculated at each and every iteration, so then therefore, this matrix J4 will not be a constant, it will be a it will actually change from iteration to iteration. So, then therefore, we have to take the inverse of this matrix J4 at each and every iteration, and as it is, as we know that this inversion process of a matrix always a very time consuming process. So, then therefore, here also this a lot of computation is necessary, but in this, because this B double dash matrix is a constant matrix, so then we can simply pre-calculate its inverse and store it, and then use this stored inverse matrix for each and every iteration. So, then therefore, at each and every iteration we avoid the necessity of inverting any matrix, thereby making this each and every iteration quite fast. So, then therefore, we write this final equations, and these final equations are that the final equations are that B. So, the final equations are that B dash into delta theta is equal to delta P, and B double dash into delta V, sorry, this is delta P by V vector, B double dash into delta V is equal to delta Q vector. So, B double dash matrix, it has got a size of n minus n cross n minus 1. B double dash matrix has got a size of n minus m cross n minus m, but both these matrices are constant matrix. So, then therefore, at each and every iteration to update delta theta and delta V, what you have to do? We have to simply multiply the inverse of this B dash and B double dash matrices, which are already pre-stored, with the most updated value of delta P by V vector and delta Q by V vectors, thereby making this entire load flow algorithm quite fast. That is precisely why it is called fast decoupled load flow solution. It is fast because it is fast So, fast decoupled load flow. It is fast because constant B dash and B double dash matrices are used at each and every iteration. At each iteration, and it is decoupled because it is following theta p and QV decoupling, because of theta p and QV decoupling. So, that is why it is called fast decoupled load flow method. So, then therefore, in the algorithm what we do in the algorithm is very simple, that we first read the bus data and etc., and then we form these B dash and B double dash matrices. Then we take their inverse and we pre-store these inverse matrices. After we pre-store these inverse matrices, then we simply proceed in the same way as we do for Newton-Raphson polar method, that first we check for all these reactive power violations of all these generators. If any generator violates the reactive power limit, so then that particular bus is changed from PV to PQ. So, accordingly these dimensions of delta Q vector would be changed and this dimension of delta V vector would be changed, and accordingly this dimension as well as the element of B double dash matrix will also change. I mean, this is the only modification. In case there is no violation is there, so then therefore this same B dash and B double dash matrices can be used. So, then utilizing that we update delta theta and delta V and then keep on doing till this convergence is achieved, and we have already discussed how to check for this convergence. So, then therefore, we are not repeating it here. So, now let us look at a very simple example, that is same example. So, in this example what we have, that we are using the same 5 bus system which whatever we have already used. So, this is the Y bus matrix. So, whenever I am saying that it is Y bus row 1 is to 3 1 colon 3. So, in the first part only the first 3 columns are shown, and in the second part at the bottom last 2 columns are shown, and we have got already 5 rows here, we can see here. So, then therefore, actually this Y bus matrix is nothing but a 5 cross 5 matrix, which it should be because we have got a 5 bus system, and we know that the dimension of a Y bus matrix is always equal to the number of bus. So, from this Y bus matrix we form this B dash and B double dash matrix. This is nothing but the negative of these elements. So, then for example, for this 2 2 you see you have got this imaginary part is minus 13.0138. So, then therefore, the first term is plus 13.0138. Similarly, all the other terms have been calculated. Please note that in this case, this whenever we are actually forming this B dash matrix, our indices will go from 2 to 5. So, then therefore, we have to only concentrate on this part, that is from second row to fifth row as well as from second column to fifth column. So, we have to take that part. So, accordingly we have formed B dash matrix, and here also we have formed B double dash matrix, because we have got 3 generators in this system, bus 4 and bus 5 are nothing but the PQ bus. So, then therefore, because as there are only 2 PQ buses, so then therefore, this dimension of this B double dash matrix should be nothing but 2 cross 2, and but this same way that, so then therefore, this matrices would be this and this with this negative sign, and that is precisely what we have got. For example, here it is here minus 10.7227. So, in B double dash matrix it will be plus 10.7227, and similarly other elements are there. And with this then we follow this algorithm, and then we have got this result. And if you compare these results with the results obtained earlier with NRLF polar and NRLF rectangular, you will find that these results are identically same. Only difference is that is number of iteration has increased. You may wonder that we have been saying that it is quite fast, but then here it appears that the number of iterations is still more as compared to the Newton-Raphson polar coordinate. It is true that this number of iteration is still more as compared to this Newton-Raphson polar coordinated, but the time taken for each and every iteration is much less as compared to that taken by NRLF polar technique, because in this FDLF technique we don't have to take, we simply do not have to compute the matrix inverse at each and every iteration. So then therefore, as we have discussed, that each and every iteration this process is very fast because we don't have to calculate this inverse of the matrix. On the other hand, in the NRLF polar method, we have to calculate the inverse of this entire matrix, that is J1, J2, J3, J4, that is entire Jacobian matrix. So it is a big matrix, especially if my system is becoming larger and larger. So at each and every iteration we have to take the inverse of a very big matrix. So then therefore it will make the iteration, each and every iteration, quite slow. So then therefore, as compared to this NRLF polar, although the number of iterations taken by the FDLF is more, but the time taken for each iteration taken by FDLF is much less, thereby making it quite fast. So that is the end of it. So with this we complete the discussion of AC load flow. So from next lecture onwards we would be looking into the other aspects of this course. Thank you.